Afternoon, depending on what time of or day it is, wherever you are in the world. I'm delighted that so many people are joining us tonight because we have a very distinguished speaker by the name of Orlando Rojas. Orlando is a professor and Canada Excellence Research Chair at University of British Columbia, and he's also the scientific director of the Bioproducts Institute. He has a rather unenviable position of being located in 3 different departments: the Departments of Chemical and Biological Engineering, the Department of Chemistry, and the Department of Wood Science. I always thought one department is enough for anyone. He is internationally renowned for his work in bio-based and sustainable materials and soft matter. He's got many prestigious honors, amongst them the Anselm Payen Award, which is the highest recognition in cellulose and renewable materials research. He's an elected fellow of both the American Chemical Society, dating back to 2013, and the Finnish Academy of Science and Letters, dating to 2017. He's held a number of titles, and I've noticed they've become progressively bigger and bigger. So he had the inaugural North Carolina State University Faculty Scholar. He also had the Finland Distinguished Professor, and now he's the Canada Excellence Research Chair, and presumably the next one will be the Global something. He's a recipient of the European Research Council Advanced Grant, which is one of the most prestigious research grants in Europe, and he maintains collaborations with universities in Europe, South America, China, and Malaysia. He's a member of the selection committee for the Marcus Wallenberg Foundation, and that awards the Marcus Wallenberg Prize, which is the most distinguished prize in forestry research. He holds scientific advisory roles for several organizations, including the Max Planck Institute of Colloids and Interfaces, the Valued Project with Imperial College, Bristol and Cambridge in the UK, and the Materials Institute of the University of Santiago de Compostela. He's an emeritus editor of the Journal of Dispersion Science and Technology, and an associate editor of ACS Biomacromolecules. For those of you who are interested in numbers, his numbers are really quite extraordinary. He has approximately 600 peer-reviewed publications, and he has an H-index of 104, as well as over 48,000 citations. That's 48,000 citations. He ranks amongst the top 1% of researchers globally in terms of citations, according to Clarivate and Web of Science. So we're really honored to have Orlando here to talk to us about his research, and he'll be talking about bioinnovation, how it accelerates through a cross-disciplinary framework, and he'll maybe explain about those joint appointments in 3 different departments. Over to you, Orlando.
Thank you so much, Dr. Ines. No better distinction than your Nobel Prize with the group and the team that in 2007 received such distinction, right? And that's something I remember when I read about you, John. Okay. And also very happy when I was actually being phasing out from Finland to come to Vancouver. We have a lunch. Maybe you remember, and that lunch, I enjoyed very much our conversation, and since then, John, we have been in touch from time to time. Very pleased to be here and very pleased to be with this community, the Asian Pacific Forestry Education Coordination Mechanism. It's a long word, but I think it's very important that we grow, nurture, and continue building the collaborations and the multidisciplinary work with our colleagues in Asia. So I make that emphasis in this image that I created with ChatGPT that shows people collaborating together, focus on a given goal, very centered, very driven to find solution to a problem, right? And today we have many global challenges, and global challenges, I always say, require global partnerships and joint work. As indicated, my name is Orlando, and there you have information about my website, my email, and you can also use the QR code to contact me. I will be very happy to meet with you when you come to this neck of the woods in your trips in Canada, in the beautiful city of Vancouver. And this center, of course, welcomes you all within the University of British Columbia. I want to bring that up. We live in a beautiful place. It's a beautiful city that is surrounded by clean water, very clean air, and of course, the forest resource. And this is very important. We need to take care of the places that surround us. And there are many threats that we don't even see in these beautiful images. One of those is the issue of the microplastics, small particles that are very abundant in the soil, in the air, in the water. Nevertheless, very difficult to detect and very difficult to avoid. So microplastics has grown into a big issue. And this is not the conversation today, but this morning I was meeting with some people discussing the big challenge of the microplastics in our health. And what we find is that there are many nature-based solutions to the solution of the microplastics problem. That relates actually with the forest products industry, bioproducts industry. We really need to rethink how to use and reorient our efforts so that we solve some major challenges. And of course, that include in our jurisdiction the issue of the fires, the wildfires, the climate change, the issue of infestation. But of course, all this inserted in a market, in a public discourse, and with also continuous policy shifts. So we're looking into having an environmentally and sustainable economy that is viable and that makes us healthier. We need to work on research on wildfire resilience, biodiversity, integrating the community and finding better ways for fiber utilization, but always keeping central the social stewardship and investing in the future of bioproducts industry. And for that reason, I will start commenting a little bit about the need for defossilization and circularity. Before going to that topic, I want to very briefly introduce what we do here in UBC, in the School of Forest Science and in Applied Sciences, as well as Sciences, where we have the so-called Bioproducts Institute. We call it BPI. In BPI, we have a state-of-the-art research and resources infrastructure with the mission to unlock the power of nature to create positive impacts in society. That's what we do. And for that, in UBC, in the BPI, we have these focus areas from biocatalytic transformation, the development and research in bio-based polymers and carbon materials that have become so important these days. Also, the utilization of nanocelluloses and other bioparticle technologies. And as well as the more system analysis, biorefineries, and systems that are very important, but all keeping in mind the social, economic, policy, regulatory factors. So these are the themes or subject areas in the BPI, where about 60 professors that are shown in this slide are very active together with their students. So in the Bioproducts Institute, we have quite nice multidisciplinary framework, and this is the title of my conversation. Here we have a group of people coming from medicine, material science, chemistry, architecture, forest science, chemical engineering, all working together. And because we work together across the disciplines, in the last 4 years, you can notice here a little report about our impact as far as securing funding for research, as far as all the events that we have designed and delivered, the number of publications that amount to 2,500 publications in 4 years, as well as all the students, postdoctoral fellows, and graduate students that are involved in the BPI. So it's really an amazing ecosystem for research, and I would say that is a world leader. But the more we connect with the world, with the globe, with partners in Asia, I think the impact will be even bigger because, again, we need cross-disciplinary framework. In that institute where I'm director of, we have also my own research group, and these are the faces of my researchers. As you can see, it's a team also very multidisciplinary, people in physics, material science, chemistry, chemical engineering, forest science, and also design, industrial design, working together in a very cohesive manner. So that's our group, and I want to acknowledge this presentation to my group members because at the end, it is their research, the one that I'm presenting today. So the first point that I want to make is that of the renewable carbon. It is clear that in the future, we will need to reduce our dependence on fossil carbon, on petroleum, and rather start to take a better look at the carbon that is produced by the sun, carbohydrates, air, CO2, in the way of the carbon that is fixed by biomass or the carbon that we recycle. That's what you see on top in this figure. And that carbon we call renewable carbon. That renewable carbon is the carbon of the future. And again, this is something that is nature-based. And since we started to talk about microplastics, this can be a solution to this very large threat in the future, the effect of micro and nanoplastics in our bodies. I know that most of you are aware of this very important aspect. But beyond the microplastics, of course, there are many other reasons related to climate and also the environment, where we need to think about the replacement of fossil carbon. So the idea here is not to eliminate carbon because we need carbon. Our society is built around carbon. The idea here is defossilize the carbon, meaning defossilization, replace the fossil carbon by the carbon that we produce from biomass, from CO2, using synthetic biology, as well as investing more and more in recycling. And this is the situation today, 2020. Most of the carbon that we use, measured here as 550 megatons of carbon, embedded carbon, is what we use. It's 88%. And the goal is on the future, in this timeline, that carbon needs to be reduced. And by 2050, we're talking about a very minor amount of this fossil carbon. So we're talking about defossilization, replacing this carbon by other type of carbon. And exactly what I indicated earlier, that carbon will be the carbon that is coming from bio-based sources, 20%, the carbon that comes with CO2 in the process of fixing CO2 in new materials. Very important, the carbon that we can recycle. More than 50% of that carbon in the future will be recycled. This is a solution to the defossilization. And I think very clearly, when we look at the bio-base on the top, the 20% of the total carbon that we need will come from plants, from agricultural waste and residues, from trees. So this is the problem and the challenge that we have today. And the driver to this change is in bioinnovation. And for bioinnovation in the area of the circular bioeconomy, we need to incorporate green chemistry and sustainability concepts, advanced materials and biomimetics, biofabrication, synthetic biology and genetic engineering, artificial intelligence and computational biology. But nothing will happen unless all these fields are taken by collaborations across disciplines. And those can also be done across countries, across boundaries. So this Asian Pacific network, in my mind, is very important and needs to nurture such collaborations. Today, I will be talking about advanced materials and biofabrication. These are the topics that are in bold letter there. And I will try in the next half an hour to explain some of the concepts. In this audience, I hope that you maybe connect with the idea nowadays that we are advancing in the area of the use of the forest resource, wood, and also agricultural materials, agricultural waste, to produce these beautiful structures that are called nanocelluloses, cellulose nanocrystals, cellulose nanofibrils, also bacterial cellulose, as well as nanospheres and nanoribbons. These are examples of different nano and micro scale structures that we are currently using. And many of you in this community are aware of these plant-based materials that make part of the cellulosic fibers and hierarchical structures. There are other nanocelluloses that are maybe less obvious. We don't need to reduce the size of a tree or wood to arrive to these nanomaterials. There are nanocelluloses that are present when we put together two pieces of wood and we partially dissolve the wood to be able to then glue two pieces of wood together. This is the less obvious nanocellulose that exists at the interface between those objects that you see in the bottom of this slide. So these are very beautiful nanotechnologies that have been developed in collaboration between Northeast Forestry University and UBC, as well as the less obvious nanomaterials that are produced by carbonization of wood. In the right of this slide, in the bottom, I put the example of super black materials that absorb light and in a very powerful way. And that process of light absorption leads to very interesting materials that can be used for preservation of energy and for the conversion of sunlight energy into thermal energy. These are also product of collaborations. So I want to insist that these examples that I'm just explaining come from two types of nanocelluloses mainly. Nanofibrillar cellulose, as shown here on the left, in an atomic force microscope, we can see the fibrillar structure on top. When that structure is mixed with water, it forms a hydrogel. That's the number one. And the second one is a microbial cellulose, one that is not produced by trees, but produced by microorganisms. I would like to make emphasis about these two types of celluloses and put some examples. And in these examples, I will, as I promised to you, I will be highlighting the power of collaboration. So let me just then walk you through the examples that I want to share. The first is a collaboration with art and designers. In this case, two of our former students in Finland were very engaged in the production of coatings, like what you see in the wall on the back, that was in an exhibition in a design chair or exhibition in Helsinki, with different numbers or names, in this case for interior design. So these are pieces of interior design where nanocellulose is used to create beautiful colors that don't require dyes or pigments, but are colors that are produced because of the nanostructure of cellulose. And that require the expertise of chemistry, but also artists and designers. This is just the first example, but I will share with you others. The case of Urs Dierker, who you see in the second frame. He is a custom designer from the movie industry. And he came to our labs also with the desire to make a change in the industry, in the cinema industry. And he was looking into creating materials like the one that you see on the very top that also have beautiful clothing and colors that are produced from biodegradable materials, mainly cellulose materials. And this is the case of a collaboration with a custom designer. A third example is the case of a fashion designer, in this case, Maria Inchner, who used to work for a very famous company called Vera Wang. This is a high fashion company. And she also collaborated with us in a project where she envisioned the production of a new generation of textiles using a completely different approximation or methods. Another example of collaboration across disciplines. And I will talk more about her company in the few slides that will come. A fourth example, in this case with a composer, music composer, Andrea Mancianti, who created some interesting helmets that contain biofilms of bacterial cellulose that allow for us to manage sound and sound propagation in music, also together with light. An example of a collaboration with, again, a music composer. And all of these are already shown in exhibitions, in art exhibitions and fashion or museums. So it's very interesting that we're working across the disciplines, not only in the box of chemistry, material science, and forestry, but we are crossing the disciplines to interact with other people that bring new ideas. I will have here 4 more examples, if I may. This is a collaboration with Japanese craft people, and looking into the use of urushi, a resin that is exuded by a special tree in Japan to create coatings in ceramics. And this was a quite nice exchange that we have with Japanese artists. Or the production of cellulose filaments by our industrial designer Ayako Takagi, who took paper or bacterial cellulose and using the technique of Kami Ito, rolled those papers into filaments like the ones that you see in the image in the second frame. Finally, 2 more cases, a media artist that used virtual reality to design environments where we teach our students about the beauty of the forest and the utilization of cellulose. And finally, an socio-ecological artist, Colleen Flanagan, who collaborated with us to look into the coral reef restoration in the sea by taking a look at ways to produce threads that can be used to tie coral reef and the seeds for coral reef in the ocean. So all along in all these examples, I have tried to show you that we need to collaborate across the disciplines. And if we do so, I think we can be quite successful to achieve quite interesting outputs that are very innovative, that connect with society, that communicate, and that allow us to produce better science with more impact and also to reach to society. Because we as a scientist sometimes we fail to reach to society. We need to connect with the public to help in the public perception about plastics and the need to adopt nature-based materials. And what better way to connect with society than using these tools like the ones that I have shown via collaboration with designers, artists, and people, experts in different disciplines. So in the next example, I will go a little bit deeper in one of the cases that I show where cellulosic fibers from the forest and nanocellulose were combined to create the solutions. And I'm referring to the case of this case of Maria Inscher, who came up with the idea that we need to change the status quo in the textile industry. As an output of this collaboration, what you see in the center is a shoe top. It's a design, it's a prototype that was designed by her team together with us to convey an idea and start a company that is quite interesting from the impact that this company will have in the future. So we created together with her these ideas, and after filing intellectual property and invention disclosures with the team, you can read the details in such patents. We created a way to transform cellulosic fibers and nanocellulose in 3D shapes for the clothing and fabric industries. This is very important because the textile industry is one of the major polluters of our environment. They are very resource intense. They require a lot of water and they create a lot of water pollution. They generate a lot of waste and they have very large amounts of embedded carbon, fossil carbon. So this is a major problem that also brings social angles in the industry, the social aspect. And many economies depend on this industry. The problem here is that there are many steps in the process. You can have the production of the yarn, the dyeing, the weaving, and then the clothing manufacturing. And that can happen in many different places around the globe, around the world. Therefore, this is very energy and environmentally intensive. In other words, we're looking here at this issue that I present on the left, the case of multi-purposes until we have a final shape or a final material. So the main driver here is to go more into the right way. What you see on the right is directly going from the fiber to the end product in one step. And to achieve that, then we look into processes that involve 3D forming. These are the concepts that we use at the time. Initially, to look into bodies, to 3D print after scanning a body of a person, and to look how we can deposit the cellulosic fibers on those screens to produce wearable clothing material. So that's what you see on the top. The the molds that were used are seen on the right, and the type of fabric that was created was the one that you see in the video, where we directly use cellulosic fibers like in paper, but using the magic of the chemistry, we make that fabric to be water resistant and washable. In fact, those garments can be put in the washing machine and reused. So it's a direct one-step process to produce a clothing material that you can put on your body. That's the type of development that we have together with the company that is called Simply Fiber. Now they have already started to produce this after prototyping in larger numbers, in larger volumes. And this is an example of an exhibition in London. They shifted a little bit from the wearables in the body to shoes and shoe tops, like what you see here, that are very beautiful from the concept of the three-dimensional design, the color, and others. But what I want to highlight here is the use of forest fibers, like in paper, but in a new, completely new use that is a result of interactions between fashion designers, chemists, forest scientists, and chemical engineers that are able to put the process together. Collaboration is the key. And this can mean the transformation of the industry so that in the future we can see more of these bio-based materials. Now they are independent and they are scaling up their production. Very nice example of what we want to advance in our area. I will skip some slides here, and I want to go directly to my second case. So allow me to very quickly go to the case of bacterial cellulose. So this is different cellulose in the sense of the structure compared to the plant-based cellulose, but I bring it because it's also a very interesting concept that comes also after very interesting collaborations. Bacterial cellulose is produced by microorganisms, and some of you maybe are aware and know products that we have in the food industry, like nata de coco. That's the same material. It's a cellulose, but it's not produced by trees or plants. It's produced by microorganisms. And we have become very interested in this concept. And I want to here place once again two cases or one case about the use of bacterial cellulose that, by the way, can be produced, this bacterial cellulose can be produced in synergy with the forest product sector, because in the forest product sector we have a lot of sugars, and those sugars can be used as a culture media for the growth of microorganisms to produce the cellulose that you see in this slide. Anyway, here is a case that I also mentioned earlier, the composer, the music composer, that together with us developed this helmet for virtual reality when we have sound vibration, because bacterial cellulose biofilms are very interesting materials as a speaker model for sound management. So that's one case. And the other case is developments like what you see here also, by the way, in the design of a shoe top by using microbial nanocellulose in 3D shaping. And this is a case of another footwear concept by a company called Modern Synthesis. Here you can see in the slide. Which is based in London, and I happen to be related to them. But the point here is, once again, here we have a multidisciplinary team of biologists, chemists, and experts in cellulose that can put together these concepts to bring a message to society. And this is something that was in an exhibition in the Vancouver Art Gallery that you see in one of the columns here in the city of Vancouver. All along, we're talking about cellulose and the interfacing between scientists and designers, and this is what I wanted to highlight. I would like to go deeper into bacterial cellulose because it's a very interesting concept, and maybe some of you will appreciate the concept because I know that the audience in this seminar, part of the audience at least, is very interested in biotechnologies. And let me expand here a little bit about this topic. So here we have the microorganisms. It's an acetic acid bacterium that produces cellulose as a way to protect itself, protect against UV light, antibiotics, or physical disturbances. It produces cellulose as a biofilm, and that biofilm that grows by aerobic process at the culture medium air interface looks like what you see on the right. We have a biofilm that is filled with cellulose fibrils, and you can notice the bacteria of the bacterium in some of the rod-like larger materials or particles that are there. These are the bacteria. And this is quite nice because you can very easily just provide the bacteria in a culture medium where you put sugars and the nutrients that you need, and then the bacteria will produce the cellulose, as I have explained before. In this case, we use a strain whose name is Comagata Abacter medelinensis. This is from a collaboration we had maybe about 15 years ago with a scientist in the country of Colombia in South America who discovered this strain in the fruit market of the city of Medellin in Colombia. Since then, we have used this strain to produce the bacterial cellulose as the one that I show now. And that bacterial cellulose makes biofilms that are similar to what I showed earlier about the paper-like material that we use in shoe tops. But in this case, it's a material that is extremely strong, very highly interconnected, very beautiful, and very interesting for the future. So I'm very interested to look into biofabrication, the use of microorganisms to produce three-dimensional shapes. And one experience that I had last year, quite interesting, was to see what is happening in China, in the industry in China, in this area. And one visit that we had with Dr. Song is the company that she owns, where this type of biofilms are produced continuously in a very large scale to produce, in this case, biofilms that have a cubic shape and they are used in food. This is a company called Hainan Yegu Foods that have different facilities around China. And I was very impressed to see how this now has entered a scale-up process where this can be produced in large volumes, at least for food applications. Anyway, here we have these biofilms of cellulose, and I like to refer to the process of biofabrication, to the process where we take the microorganisms and we make three-dimensional shapes. And I want to spend now a few minutes to explain how we do this, and you can learn more details in the publications that we have produced, and they are shown in the bottom. But the idea here is very simple. Remember that I told that these microorganisms are aerobic. They need air, they need oxygen from air, typically. And that happens when you have the culture medium exposed to air. But one thing that we discover is that we don't need air. One option is to take the culture medium and put it in contact with a mold, like what you see here, in a mold that is super hydrophobic on the right. And then if you have the culture medium shown here in blue in contact with the mold that is super hydrophobic, there will be clusters of air that is trapped. That air is called air plastron. And that air that is trapped between the culture medium and the solid is enough for the bacteria to take, metabolize, and produce cellulose. So by using solid molds, we don't need the air interface, as we know. We don't need culture medium air interface. We can use culture medium solid interface to produce biofilms of cellulose. One example of what I'm explaining is to produce three-dimensional objects that can have very intricate properties and shapes, like the one that you see here. This hollow fractal branch structure is very difficult to produce by 3D printing, but by using biofabrication, it's rather easy to produce these materials in 3 dimensions. Here I want to note that actually the production of biofilms is quite competitive if you think about the synthesis process, the area that is needed for manufacture a piece of an object, and the time it takes to the bacteria to produce the biofilm. So I don't think I'm too far incorrect if I say that in the future, biofabrication and the use of microorganisms can supplement the fabrication that we know via the biosynthesis in plants. I think in the future we will have the two hand in hand, trees and also biofabrication. Of course, the challenge in biofabrication is the cost of sugar, for instance, right? But otherwise, here, sugar or nutrients in the culture medium. But I think in the forest industry, we have excess of those materials. Anyway, I will show an example of what can be possible to make with those biofilms. And by using the molds that you see here on green that are 3D printed, we can grow bacterial cellulose biofilms with different shapes and designs, as what you see here. Some of those designs can be eusectic meshes or structures. Eusectic means structures that when you stretch, they become thinner in the cross direction. These are the ones that you want to have in biomedical implants and in applications of high-end applications, for instance, that are in contact with your body, in your elbows or in other parts of your body. It's called eusectic materials. And those eusectic materials, again, they deform in a special way. And you can do these designs, by the way, with designers, and then produce meshes that can be used in high-end applications. One of those applications that we tested was trying the hernia treatment of animals in vivo, or the treatment of a condition that is very typical nowadays called the prolapse. It's sagging organs that need to be kept in place in our body, shown here by the mice, and the fact that if you have a hernia, then the intestines and the muscles will not be well connected, and then we will have sagging, like also happens in the treatment of prolapse. And what we found is that the current solution to this problem are polypropylene meshes, the so-called Gene Care TBT Exact. There are meshes that are used today in medical implants, but if you see the metrics on the right, they imply foreign body reaction, granulation tissue formation, and scar tissue formation. So they are not too effective in our body. But when we use a solution based on cellulose in the implants that I show, then together with biomedical engineers, we learn the bacterial cellulose meshes, like the ones that I show, are very effective in having 100% behavior or performance for this type of meshes. So based on this, we have filed a number of patents, and we hope to see this at some point in the future being used in our bodies. But the transition is, of course, a very long transition for putting these implants in the market. I want to give a final example of what is possible. And in the audience, in this group, I think one of my students or some of my students are present, and maybe they can explain this better than me. But it's another discovery. And this is that we don't need the solid liquid interface. We can go to the oil liquid interface to create three-dimensional objects. And that's what we call biofabrication under liquid. So in this case, what we have is a culture medium in blue, and we use an oil, and that oil can dissolve oxygen. There are many different oils that are capable to maintain air or oxygen dissolve. And that means that if we put the two fluid phases in contact, the oil and the culture medium with the bacteria will be able to access the oxygen from the oil and produce the biofilm at the interface between the oil and the liquid interface. Professor Yi Lu, now in China, actually was behind this concept. And now we have a number of students working on the liquid biofabrication. The type of biofilms that you produce by under liquid fabrication is similar to the ones that you produce with the air culture medium interface. So the first column is the one that is produced with air. The three on the right are those that are produced at the oil-water interface. We use perfluorodecalene oil, silicone oil, dodecane, and other oils. And we observe that the biofilms of cellulose are very good quality. And then, in fact, we observe that the oxygen solubility of those oils, as they increase, then the amount of the biofilm that is produced also increases. So here you can see in this plot cyclohexane, hexane, hexadecane, dodecane, and other oils, right? But the best oils are those that are very good at dissolving oxygen, like silicone oils and perfluoro oils. So this concept is very simple, very simple. And the current ideation is that if we mix the oil and the water interface in emulsions, like water in oil emulsions or oil in water emulsions, we will be able, or we are already able, to create capsules, foams, and other structures on the liquid fabrication. So this really is opening a lot of opportunities in the area of biofabrication. Okay, so I think here there are many advantages. One, we don't need to use liquids exposed to air, therefore we avoid evaporation. We can carry out biofabrication at the oil-water interface, for instance, using the concepts that I just showed, but also using emulsions. And this can be done in processes that can be continuous. So it's a beautiful opportunity that we hope can be expanded in collaboration in the future. For details about these concepts, you can read the literature. But once again, I want to emphasize that all these developments happen because cross-disciplinary collaborations. Today, we are expanding this to gel-in-gel printing. Here we use cellulose from plants, cellulose from wood. We combine cellulose and other materials to produce liquid-in-liquid systems or gel-in-gel printing. And that allows us to produce volumetric objects that are not produced in air, but on the liquid. And that presents a number of advantages. For instance, many of these designs can benefit from the composition of the two liquids so that we produce functional materials. Therefore, we can extend and find new uses for this type of biofabrication, right? For example, in liquid streaming, aquabots, liquid beads, 3D liquid-in-liquid printing structures, we can create materials that combine graphene oxide, metal materials, metal organic framework, MXene, and others with bio-based materials. And all of these are used in advanced electronic and in advanced materials. But the secret is the way that we combine them at the interface during the printing and biofabrication process. At the end, I hope that you see the relevance and the impact of combining expertise from different disciplines. That's the main message of my talk. And in the examples that I explained to you today, we consider the case of plant nanocellulose, but also bacterial cellulose. They too, in the future, will be key elements for the future bioeconomy. And I would say that the two will be allowing us to reduce our dependency on fossil carbon and to create the materials of the future. That's my message to you. But most important, always in the design of my talk today, is that I want to press the idea that it's very important that we look outside the box. We find partnerships and collaborations, not only across the boundaries, but also across the disciplines and different areas of expertise, as I have indicated, in completely different areas. With that, I will end acknowledging the people, the students, and the research team that I'm working with, and also the funding agencies that have been very instrumental for us to advance these concepts. Thank you so much to the audience, and I'm happy to answer any question.
Orlando, thank you very much for that absolutely excellent account of the research that you're doing. I think it's incredibly exciting. You're developing areas that I think nobody could even have dreamed about at some point. I do have one, maybe just a kickoff question, and you hinted at this a little bit. Working in the lab, you find these wonderful things, but getting them into a solution for the bioeconomy, in other words, scaled up as a commercial proposition, takes a very, very long time. Is there any way of speeding up that process? Because with climate change, we don't have very much time, if we have any time at all.
John, this is a fundamental question, and we all, as a collective, as a community, we really need to think very deeply on that question, because what we do in the labs won't ever see the light of the impact if we don't design the mechanisms to adopt these materials in large scale and in large quantities, right? And here today, I present a few cases that are very unique, and maybe you can think about exotic. But I can tell you many other examples that are really very well designed in performance and cost to replace single-use plastics, to replace the textile materials that we use. And what is then the requirement for us to shift from fossil carbon to biocarbon, right? So that's the question. And there is a combination of factors. Industry is designed to process petroleum-based streams. That means that we use heat. We use heat to transform the thermoplastics that we use. On the contrary, all these materials are transformed not by heating, but using water as a medium. So what I mean is that all the processes that we know are adapted to a given raw resource. And that means that the processing schemes need to be changed. That's a major roadblock. That transition is difficult. And that means that we need to then look into the need for partnerships with government, with corporations and industry to create the framework so that this process is facilitated. So all in all, there is a lot of things that we can discuss, and I have a long answer that maybe can be more complete. But the point is, first, we need to incentivize knowledge translation, prototyping of the materials, demonstrate that the materials are cost effective, and have the right performance. And then we need to translate this into common use. That means communication with society. So all these factors need to go hand in hand. But it's urgent that we start to make that transition. It's urgent. The problem of microplastics is one example. We are consuming 5 grams of microplastics per week, like a credit card goes to our body and is accumulated in our organs, in our blood, in our brain. This will change the biology of humans. And this is because the negative effects of plastic materials that we use today. This is beyond the climate change. It's the impact in our health. We need to make a change. And there is no other solution but to use the materials that we're talking today.
Thank you. I don't see any hands up, but there are questions in the chat. So hello from Brazil, Rafael Angel. How can we raise consumer awareness about the impact of microplastics in fashion and promote more sustainable choices?
Yeah, so that's very important question, Rafael. Thank you for the question. And you see, we already know from media, we are already aware of the microplastic situation. But the way it's communicated is that we see plastic bags floating in the oceans and turtles entangled with plastics. What we don't see is that microplastics are everywhere in the cup of tea that we drink, with the plastic bags that release microplastics in the tea that we drink, or the water that we drink, or the soil that is used in harvesting the food that we eat. There are microplastics. And these are the ones that we don't see because they are difficult to see. We need microscopy to visualize. So that then begs the question why society is not making a change, because we cannot see, we're not aware. They are in large quantities but also very diluted in the ocean, or diluted in the water, diluted in the soil, and diluted in the air. We don't see, but they are creating a major problem. So we need to connect with society. That's the key challenge. And for that, that's where I bring the issue of interfacing with artists, communicators, designers, because they are the best place to bring a concept to the general media. We as a scientist were not trained to bring an idea to the society at large, but combining artists, designers, like what I presented, then it is possible for us to have a larger reach into the world society. And that's very important because a change can start with the consumption, with the consumers, and also, of course, the regulatory framework, the policies that are installed by the different governments. These are all need to be combined.
Thank you. We have another question in the chat, and this is from Zishan Tariq in China. I want to ask about 3D fabrics. What about the cost of mold and production? Also advise durability of the end product. Thanks.
Yes, that's very good question, and there are maybe different comments that I can indicate. If we're looking into fabrics, the concept here is actually quite interesting. They can be custom made for your body. So the initial ideas that we had, not yet in process, but the initial idea was to scan the body of the person that wanted to buy the garment, and then have a 3D printed mold to create that material, right? And then, of course, by using paper fibers to produce a fabric, and that fabric then can be custom made for the person, tailor made almost, right? So that process is possible, but the molds that are used, that are made by 3D printing, are molds that can be reused. They are made of polymers, and they can be reused thousands of times. So those molds are not an issue as far as the cost, because once you have it, you can mass produce the textile materials. Same for shoes. The shoe tops can be produced in molds for the different shoe types or shoe sizes, and then they can be mass produced. So it's not really a major challenge. As far as the durability, here it's very important that we think we either need to use things that are durable or recyclable. They can be, they can have a given lifetime, and cellulose in particular may not have a long durability, but at the end of the life is biodegradable. And what is better, that we know how to recycle fibers. So those products that I show, for the most part, based on fibers and cellulose, can be recycled as we recycle paper. Paper recycling is very typical. And if you think about the recyclability of paper, is quite prominent in many different countries, right? 70%, 80% recycling rate. That's amazing. Compare that to typical polymers, 4% or less, 2% recycling rates. So paper-based, fiber-based materials are the materials of the future.
Thank you. We've got time, I think, for one last question, and that is from Aksa Ali, who is in China. How do bacteria extract oxygen from oil, and what factors influence this process? What are the potential industrial applications of under-liquid biofabrication?
Thank you, Aksa. Very good questions too. So the oxygen is present in oil. Or those types of oil that I show will dissolve oxygen from the atmosphere. They carry oxygens, especially the fluorinated oils carry a large amount of oils. Maybe Aksa, I don't know if you have seen the experiments with really small mice that are led to be immersed in oils and breathe under liquid, right? Under the oil. So the point I'm making is oils can dissolve oxygen, and that oxygen is enough to be delivered to the interface for the bacteria to grow cellulose. That's enough. That's the whole concept of dissolving oxygen and making it available for the bacteria to grow the biofilm. So this is possible. Now, is it possible to replace bacterial cellulose, to replace plant cellulose in the future? Actually, there are companies that are already trying to do that. In San Francisco, there is a startup that claims that goal, actually. And I think it's challenging at the present time. It's difficult because trees are in large volume, are produce cellulose in large quantities. They are around us. This is a very cheap source of cellulose. But in the future, I can see that many advanced materials and specialized materials can also be produced by biotechnological means, by using synthetic biologies, and can be part of the solution, meaning trees together with biotechnology in the production of cellulose. So I think it's possible, but not at the moment, right? That will take quite some time. As far as other questions here about the advantage of the bacterial cellulose compared to the cellulose from plants, that's from Professor Wang. Very good question. Very shortly, the cellulose from bacterial cellulose has a higher degree of polymerization. Mechanically, is stronger and is pure cellulose, no lignin, no hemicellulose. So that's the difference between bacterial cellulose and the cellulose from trees. Of course, there are other more fine structural changes and differences in the polymorphism and the crystallinity of the material, right? But essentially, it's the same cellulose, essentially.
Okay, thank you very much, Orlando. I know there are more questions coming in, but unfortunately, we are out of time. We do try and keep these to a 1 hour session. And I suspect actually there would be questions that would go on all night if we allowed it. Thank you very much for such a wonderful seminar. Very, very inspiring. You are clearly working on solving major global challenges, and it's really encouraging to see someone who's actually doing it as opposed to just talking about doing it. So thank you, and we look forward to learning about your next fantastic development. And maybe we'll see you getting a Nobel Prize for chemistry or biology or something.
It will take ages, but super happy, John, to be here to share the seminar with you and Professor Wang Yu Wang. And the team, thank you for hosting me. I'm happy to engage with the community. It's very important that we keep working together.
Thank you. I totally endorse that. So thank you, everyone, for